Floating through space, you've probably noticed things tend to move in all kinds of directions. But to understand how they move, we need to get real with a simple idea: scalars and vectors. First, let's meet the scalars. Imagine you're measuring your speedometer while cruising down the road. It reads 16 miles per hour. Boom, that's a scalar. It's got a number, magnitude, and tells you how fast you're going, but not where. Like knowing it's hot outside without knowing the wind direction. Just pure numbers, no strings attached. Now, say hello to vectors. They're like scalars, but with more attitude. Not only do vectors give you a magnitude, they point you somewhere. Imagine tossing a ball. Vectors don't just tell you how fast you threw it. They show which way it's flying to. Speed plus direction? Classic vector vibes. So what's the big deal? Well, scalars and vectors act differently. Scalars add up like simple numbers. Got $5? Get $10 more. Now you have $15. Easy math. But vectors? They play by vector math rules. Say you're walking east at 3 miles per hour, then turn north at 4 miles per hour. Your final speed is somewhere in between those two paths, thanks to good old vector addition. You really get vectors, think about displacement versus distance. Distance is a scalar. It's a total ground you covered. You walked in a giant circle? Distance says, congrats, on 2 miles. Displacement, a vector looks you in the eye and says, cool story, but you ended up back where you started. Net movement? 0. Next, there's velocity and speed. Speed is a scalar. It tells you how fast you're zipping around. But velocity? That's a vector with direction baked in. Change direction but keep moving? Your speed stays the same, but your velocity changes. Direction matters. Vectors also come with cool tricks, like breaking into components. Imagine pushing a heavy box diagonally across the floor. The force splits into 2 parts. One part pushes straight forward and the other presses down, giving you a killer arm workout. It's like splitting an action movie scene into slow motion details. Each component plays a role. Then there's dot product and cross product. Dot products are like asking, hey, are these 2 vectors working together? If yes, the number grows. If no, well, it shrinks or goes negative. Cross products? They're like asking, what's a spin when these 2 meet? Useful for figuring out torque and angular motion. Fancy stuff. In summary, scalars give us raw magnitude, like how far, how hot, or how fast. Vectors take it further, adding direction and context to every move, every push, every toss. They rule our universe with numbers and direction. So what's the deal with scalars and vectors? Let's take a trip to the gym. You've just picked up a 45-pound dumbbell and you want to brag about it. I'm lifting 45 pounds. That's a scalar. You told me how much, but you didn't say which direction. Scalars are all about the numbers: speed, distance, mass, energy. No direction, just pure quantity. But hold up. Now you lift that 45-pound dumbbell above your head. You're pushing it up. Congrats, you've entered vector territory. A vector has magnitude, the 45-pound weight, and direction, upward. Basically, vectors are like scalars but with more sass. They care about which way you're pointing. Now let's hit some examples. Walking down the street, scalars versus vectors. You walk 100 meters, that's a scalar. Just distance, no direction. You walk 100 meters north, boom, now it's a vector because it tells me the distance and the direction. Speed versus velocity. Speed is how fast you're moving, like, I'm running at 10 meters per second. That's a scalar. It doesn't care where you're going. Velocity? That's speed with an attitude. I'm running at 10 meters per second east. Now we know how fast and in which direction. Breaking down forces. Imagine you're pushing a heavy box across the floor. You push diagonally, but what's actually happening? Let's split that push into parts, components. Part of your force pushes the box forward, and part of it pushes it downward against the floor. Breaking vectors into components is like showing all the hidden moves in a dance. It reveals what's really going on. Vector addition made easy. Think about walking 3 steps north and then 4 steps east. What's your total movement? You could say you walked a total of 7 steps, but that doesn't tell the whole story. Instead, treat it like a right triangle. Your net movement, displacement, is the diagonal across the triangle, found with Pythagoras. The square root of 3 squared plus 4 squared equals 5. That's 5 steps northeast. Vectors love to be precise. Projectile motion. Throw a ball at an angle, and it follows a curved path. Why? It's all about vectors. One for its horizontal speed and one for its upward motion. Gravity is going to bring it back down, of course. When you toss it, gravity acts as a vector pulling it downward. Together, these vectors create that nice arc in the air. It's like a dance between upward and sideways movement. Vector multiplication, dot product and cross product. Sometimes vectors don't just want to hang around, they want to interact. Enter the dot product and cross product. The dot product finds how much two vectors align. Picture pushing a box straight ahead. If you push in the exact same direction as the box moves, all your effort counts. But if you push at an angle, only part of your effort goes into moving the box forward. The dot product gives you that useful part. Mathematically, it's the magnitude of the vectors multiplied by the cosine of the angle between them. The cross product, on the other hand, gives you a whole new vector that's perpendicular to the original two. Imagine spinning a wrench. The twisting force you apply creates rotational motion, torque, thanks to the cross product. Real life example, airplanes and wind. Ever wonder why pilots care so much about wind, speed, and direction? It's because vectors rule the skies. Suppose a plane flies at 200 miles per hour north, but encounters a 50 mile per hour wind blowing west. The plane's true velocity relative to the ground is found by adding the velocity vectors. It ends up moving diagonally. Using vector addition, pilots know how to adjust their path to reach their destination accurately. Unit vectors and direction. You know vectors have direction, but sometimes you need a standard way to talk about direction alone. That's where unit vectors come in. They have a magnitude of 1 and point in specific directions, like north, east, up, etc. In physics, we often use I hat, j hat, and k hat for unit vectors along the x, y, and z axis. These help us describe any vector as a combination of these directions. Think of it as building directions using simple blocks. Vector fields and applications. Vectors aren't just about moving objects. They also describe fields. Ever heard of electric and magnetic fields? They tell you how forces act around electric charges or magnets at every point in space. Gravitational fields. Same idea. If you drop an apple, it falls because Earth's gravitational field points everything toward its center. Fields let us predict how things will move and interact over large areas. From designing motors to predicting weather patterns, vector fields are everywhere. Equilibrium and forces. When all forces acting on an object balance each other out, the object is said to be in equilibrium. Imagine hanging a picture on a wall. The tension in the string and the force of gravity must be perfectly balanced for it to stay still. Using vectors, we can figure out exactly how much tension is needed for equilibrium. In engineering, understanding equilibrium helps us build stable structures. Bridges, buildings, and even roller coasters rely on this concept. Relative velocity, boats and rivers. Another fun scenario. A boat is crossing a river with a current. The boat heads straight across at 5 miles per hour, but the river flows at 3 miles per hour downstream. What happens? The boat's actual path is diagonal due to the combination of these velocities. To find the boat's real motion, we add the velocity vectors. This concept helps us understand everything from swimming in a current to navigating spacecraft in orbit. More on vector components. Breaking down motion. Vectors can be broken into their horizontal and vertical components. Why is this useful? When throwing a ball, the horizontal motion stays constant, assuming no air resistance, while gravity acts only on the vertical component. This separation makes it easier to predict how the ball moves through the air. It's why physics problems often look at x and y directions separately before combining them. Transformations and rotations. In computer graphics, vectors are used to rotate, translate, and scale objects on the screen. Want to rotate a 3D model of a spaceship? Vectors help define how far and in which direction each part moves. By using matrices, collections of vectors, we can apply transformations to whole objects, making them move, spin, and resize. Vector trick. Mass versus weight. Mass is a scalar. It tells you how much stuff there is, like, I weigh 154 pounds. But weight? That's a vector because gravity gives it a direction, downward toward Earth. Your mass stays the same everywhere, but your weight changes depending on gravity's pull, like on the moon. Magnitudes and directions recap. To wrap it up, scalars give us quantities. Vectors give us quantities with direction. They break down into components, combine in complex ways, and shape everything from the forces around us to the motion of galaxies. And remember, vectors can't help but show their direction. They're always pointing us somewhere. Scalars give you the numbers, vectors tell the full story.